Hello and welcome to this video on using the quotient property to simplify radical expressions. So in this video I'll introduce you to the quotient property, or sometimes you might call it the fraction property. When you hear the word quotient you should think fraction, ratio, division. So I'm going to introduce you to the quotient property for radicals, and then go into some examples where we're going to be using that to simplify a radical expression, right? An expression with some sort of nth root in it, right? A radical symbol. Alright, so on my first page, I'm going to just show you what this quotient property is. So we have again, the quotient property for radicals. Alright, and here's what this states. If I take the nth root, right, the nth root of some, say, radicand a, some number a, divided by, right, quotient, division, right, divided by the nth root of another radicand b, this is equivalent to, it's going to be equivalent to a single nth root, right, the one radical symbol, the nth root of, and then the radicand over here is just the ratio of the radicands over here, a divided by b. Okay. Now, this isn't always true. I have to write some little caveats down here. This is true as long as these numbers are real numbers, right? As long as the nth root of a and the nth root of b are, real numbers. Additionally, b cannot be 0, right? You can't divide by 0. Can't have 0 in the denominator. And any root of 0, any nth root of 0 will be 0. Alright, so all this means is that you have to, again, as in previous videos on the product property, you have to pay attention when you have even roots, right? When you have an even index, square root, fourth root, sixth root. Because if you have an even root and one of these radicands is negative, then you have a non-real number, and this property does not hold. All right. So this property is a property of real numbers only. So for example, if I saw this square root of, say, 50 in the numerator, divided by the square root of 2 in the denominator, I could use the property because both of these numbers, the square root of 50 in the numerator and the square root of 2 in the denominator, they are both real numbers, right? They are even roots of non-negative radicands, even roots of non-negatives. And because they're both real, again, that means that we can use the property. Alright, so if we can use the property, I divide these two square roots, I get another square root, right? Notice the root, the radical doesn't change, the index doesn't change throughout the property. And the radicand of this square root will be 50 divided by 2. Right? The numerator radicand divided by the denominator radicand. And we can go further and simplify that fraction, right? 50 divided by 2 is positive 25. And remember, this is what's the non-negative square root of 25. That would be positive 5 here. Whenever you see these symbols with even roots, even indices, your result should be non-negative, right? So this would be 5 here. But just pay attention, do I have real numbers or not? And if not, then you can't use this property. Right? So another example, if I took the fourth root, say the fourth root of 38, and then tried to divide that by the fourth root of negative 19, the numerator, the fourth root of 38, that's a real number, but the denominator, right, you have an even root of a negative number, that is not a real number, which is a problem. That tells me that we cannot use the property. Right, we cannot use the property. Alright, so I'd simply say this result had a non-real part to it, wasn't a real number, and be done with it. I wouldn't go any further. You can't put these together and make it the fourth root of 38 divided by negative 19, or the fourth root of negative 2. Right? You can't do that. Alright, this rule only applies when the nth root of the roots of the numerator and denominator are representing real numbers only. Okay? Alright, and it goes in both directions, right? So far the two I've shown you, well, the one that we could actually use the property for, I started off with something looking like the left side where I had a root divided by a root dividing two radicals and made a single radical. It goes the other direction as well. It's an equal sign. So if you have a radical with a fraction inside, you can split it up. You can take the radical of the numerator and the radical of the denominator separately, but again, just so long as those two radicals are representing real numbers. Right, and that's what my first several examples are, where we have a radical with a fraction in it and are asked to simplify by, splitting it up. Okay. All right, so let's take a look. My first example, I have a square root, right? The index of the radical is 2. Square root of 13/49, a fraction, a quotient. Both of the, this is a square root, even root, and this is a non-negative number. The numerator is non-negative, the denominator is non-negative. So I can split this up. That's okay. These will be real numbers. The numerator would be is going to be the square root of the 13 divided by, notice how I'm making it big, right? The divided by symbol, so we know that the square roots are split. And then the square root of the denominator is square root of 49 in the denominator. And again, this is totally valid because both of these are real. The square root of a positive, the square root of a positive. Those are real numbers. And then we simplify the radicals, and I've had a video prior to this if you want to look it up on simplifying radical expressions. Right, these are square roots. Okay, so we're looking for factors of the radicands that are perfect squares. Right, things raised to powers that are multiples of 2. Right, squares. 13 is prime. You can't break down 13 anymore. But 49, so I'm going to leave that the way it is. That's not a perfect square, so that's going to stay the square root of 13 in the numerator there. But 49 is 7 squared, right? So you have the square root of 7 squared, which would again technically be the absolute value of 7, because I want it to be non-negative. But what is the absolute value of 7? That's just 7. So we have the square root of 13 in the numerator divided by, and then just the number 7 in the denominator, and this would be considered, all my radicals are now simplified. And let's just double check, like I like to do in these radical videos, with square root, with the calculator. So let's see, let's clear that out. Is this indeed equal to this? Well, let's see. Let's take the square root of, and then inside the square root, 13 divided by 49. Right, make sure it's all inside the root. That's 0.51507 and so on. And let's check this number here. We had the square root of 13 in the numerator, and then after that, right, not inside the square root, divided by 7. And look at that, that is also the same number, 0.51507 and so on. Wonderful. Okay, I always like to double check if I have time. Alright, so there's one where we could use that property, quotient property. Here's another one. Now this one has some variables in it. Alright, this one has a variable p. So when there's variables involved, I haven't been the best at this in my videos, but I do like to point it out at some point what the domain of the expression is. Remember, the domain is what's allowed to be plugged in for p. Now this is an odd root, a cube root. Remember, you can take an odd root of any number. So the radicand can be positive, it can be negative, it can be 0. So it looks like p, the value of p can be anything. And notice there's also no variables in the denominators. There's no variables raised to negative powers. So it's not like I'm going to be dividing by 0 or having 0 to a negative power, right? Those things are not allowed. You can't divide by 0, which is basically having 0 to a negative power, right? You can't have those, but that's not happening here. So it looks like p, the value I replace p with, can be any real number. Just like to mention that when there are variables involved. What am I allowed to plug in and what am I not allowed to plug in? Okay, so now that I've stated this, when you have an odd root, you don't have to worry, right? Remember, I said a second ago, you can take odd roots of any real number, and the result will also be a real number, positive or negative or 0. So because of that, we can, if we see an odd root of a fraction, you can automatically jump to using the property and say this is equal to, the cube root of the numerator of the 27p cubed divided by, and again notice I'm making this longer so it's not inside the root, it's splitting the roots, and then the cube root of the denominator of 8. Alright, so this time I'm just going to state what the cube roots are. Right now, here I have a product, and remember I can use the product property. If you want to look up that video I've had on using the product property to simplify radicals, go ahead or look up other videos or look in your books on product property for radicals. But this cube root I can split up. The cube root of 27. What to the third power would give me 27? That'd be 3. And then times the cube root of p cubed would simply be p. And there's no need for absolute values around that, right? The result doesn't need to be non-negative because this is an odd root. Right? So just simply 3p in the numerator. And then what's the cube root of 8? 8 is actually 2 cubed, so this is 2. And there you go, and that's a simplified fraction, right? The numerator and denominator don't have any common factors, so that's it right there. And again, let's test it out. So in my calculator, I'm going to replace p. Now p can be any real number. So I can let p be anything. How about 6? Alright, I'm just going to test it with p equals 6. So this expression, I'm going to enter. Right, we have the cube root of, and then in the numerator, so I'm going to put this in parentheses here, 27 times 6 cubed, right? I'm replacing p with 6. Divided by, right, so that's the numerator, 27p cubed, where p is 6, divided by, and then 8 in the denominator, and notice how it's all underneath that root, right? It's all in the radical. And that's equal to, 9. Wow, okay, I guess I picked a, well, I guess, you'll see that, 2 goes, basically any even number will give me something nice and whole, because 2 goes into any even number. So I'm getting 9 there, when I plugged my 6 in for p in the original expression. This one here, numerator around the parentheses around the numerator, parentheses around the numerator. I have 3 times p, 3 times, and again I'm replacing p with 6, divided by, and the denominator is 2. That's 18 divided by 2. That's also 9, right? Get the same value, and try it with any value of p. Plug in 5, 10, a million, plug in a fifth, plug in pi, plug in the square root of 2, whatever you want for p, and that expression should have the same value as this one here in the box. Wonderful. Okay. Next example. I've got the fourth root, again, pay attention. This is an even root. Right? That means that the number in here must be non-negative. Because if it's not, if it were negative, the result would not be a real number. So the radicand must be non-negative. All right. So that'll lead me to a statement about the domain. All right. Before I go simplifying this, again, if an expression has some variables in it, I do like to talk about what am I allowed to plug in for that variable, right? Or those variables. Well, there's only one variable here. It's this q. Again, the expression inside here can't be negative. Well, the 3 is positive. The 16 is positive, right? 3/16 really is what I have here. That's positive. And notice how q is to the fourth power, an even number. And really, if you take any real number, take a positive number to an even power, it's still positive. Take a negative number for q, raise it to an even power, a negative to an even, that's positive as well. And 0 to the fourth power would just be 0. So q can be anything in this example. Q can be positive, it can be negative, because you're going to be raising it to the fourth power, which will make it positive again, right? It'll always be non-negative. So in this example, Q can be any real number. Great. All right, so I'll keep that in mind. And again, there's no denominators that can be 0. I'm not going to be dividing by 0 for any value of Q. There also aren't any numbers to a negative power, right? I'm never going to have 0 to a negative. You can't have 0 raised to a negative power, because that's basically the same thing as dividing by 0. If you remember that negative power property of exponents. All right, so keeping that in mind, as long as, no matter what I plug in for Q, this will be non-negative, so we'll have a real number, and therefore I can use that quotient property and split this up. So this is going to be the fourth root of the 3 times q to the fourth in the numerator. Big long division symbol. This, I'm splitting the roots, the root of the numerator and root of the denominator. And then the fourth root, right, the principal fourth root, non-negative fourth root of 16, the denominator. All right, and as I did in previous videos on simplifying radicals with the product property, we have the fourth root here, so I'm looking for stuff raised to a power that's a multiple of 4, right? I'm looking for perfect fourth powers, and I have one of those in here. The fourth root of q to the fourth would just be q. And technically I should, it should be the absolute value of q though, right? Remember that, if I take the fourth root of q to the fourth, you can't just say it's q, because if you do, remember this, anytime you see this symbol with an even root, an even index, the result needs to be non-negative. Well, I said earlier, q can be any real number, so what if q is a negative number? Then you get a negative result. So remember how we fix that, right? You put it take the absolute value of it to ensure that it's non-negative, right? So the fourth root of q to the fourth will be non-negative if I just say it's the absolute value of q. Then times, you got multiplication, times, and then the fourth root of 3. 3 is a prime number. It can't be factored any further, and it's definitely not a perfect fourth power. So the fourth root of q to the fourth, I have the absolute value of q in the numerator, times, and then the fourth root of 3. And you can put a little dot for times, or just have them touching like this, right? So that's the fourth root of q to the fourth times the fourth root of 3. All that in the numerator divided by, and then what's the fourth root of 16? Well, 16 is 2 to the fourth. All right, 2 to the fourth power. So it would be the absolute value of 2. But the absolute value of 2 is actually just 2. Right? And there you have it. This guy right here. This fraction. Now let's test it out. Let's test it out. So I'm going to replace q with, again, you can replace q with anything, because our radicand in the fourth root earlier will always be non-negative no matter what you plug in for q. So I'm going to test it with, say, q is -7. Why not? So I'm going to put in the original expression. So I got the fourth root of, in the numerator, I'll put the numerator in parentheses because there's multiple factors, right? 3 times, and then -7 for q to the fourth. Okay, and then still in the radical, still inside the radical symbol, divided by, oops, I should close the parentheses. That's the whole numerator. 3 times q to the fourth, right? 3 times -7 to the fourth. And then after the parentheses, divided by, notice it's still inside the radical symbol, divided by 16. Still inside the root symbol, the fourth root symbol. Alright, so that's some crazy number, 4.606259045, and so on. Well, if I did everything right, and I'm sure I did, the value of this when q is -7 should be the same as the value of this when q is -7. Alright, so I'm going to put in parentheses the numerator. We have the absolute value of -7, right? I'm replacing q with -7. Now you can put the absolute value symbols and then put -7 in there, or just put 7, right? Because what is the absolute value of -7? It's just 7. So I've got the absolute value of q times the fourth root of 3. And I'm going to close parentheses. That's the numerator, right, when q is -7. And divide that all by 2. And look, it is indeed the same number, 4.606259045, and so on. Great. And that should happen no matter what q is. Replace q with any real number, and our original expression will be equal to that final one. But you got to pay attention again with even roots. When you see an even root, the result needs to be the non-negative root when you see that symbol. So be careful, sometimes you might have to employ the absolute value symbols. Alright, here's another one. Now my first 3 examples, I went from the square root of the root of a fraction, a radical with a fraction inside, and then split it up. Took the radical of the numerator and then divided by the radical of the denominator. This is the other way around, where I have a radical in the numerator divided by, and then that same radical, same root in the denominator, and then we're going to put them together, right, and simplify. Alright, so as I like to do with expressions of variables, this has the variable a in it. You have the square root of 12a to the 5th divided by, and then in the denominator, the square root of 3a. Well, I'm going to state off to the side here. Let's do some thinking. What values can I actually replace a with? What's the domain of this expression? Alright, well, doing a little thinking. These are even roots, square roots. So the numbers inside, the radicands inside them, have to be non-negative. Well, let's see. 12 is already not negative, but a to the 5th. A to the 5th could be negative if a were negative. Right? A negative number to an odd power is negative, and then a negative times a positive would be negative, and that would be bad, right? I'd have a non-real number there. So a can't be negative. Same thing down here. I have a positive 3 times a. If a were negative, that would be bad. I'd have a non-real number down here. Okay, so a can't be negative from the get-go, and then additionally, you see how there's this a in this denominator, right? A 3a. See, if a were 0, that would be bad as well. Because what's the square root of 0? That'd be 0. You'd have divided by 0. That's wrong. You can't have a divided by 0. That's not defined. All right, so the only numbers I can use are positive ones, right? A can't be negative, and A can't be 0. So A has to be strictly greater than 0. A has to be positive, right? In other words, A has to be positive. A positive real number. Okay, so let's keep that in mind. Know that I can't plug in negatives or I can't plug in 0 later. Alright, so as long as A is positive, these are real. Right? When A is a positive number, this will be the square root of a positive, and this will be the square root of a positive. So these will both be real. And if they're both real, then I can use the quotient property. So the square root of 12a to the 5th, divided by the square root of 3a, I can make it into a single square root, and then divide these two inside. 12a to the 5th divided by 3a. And then just canceling some common factors in this fraction, and here we have the square root. 3 goes into 12 4 times, so you'd have 4 left over in the numerator and 1 in the denominator. And then a to the 5th divided by a would be a to the 4th, right? One of the a's would cancel as a common factor, divide out to be 1. So I have 4a to the 4th. Alright. And if you break this up, we can use that product rule. This is the square root of 2 squared, right? 4 is 2 squared. If I think about, we're doing square roots here, so if I think about how I have a perfect square, right, try to write these things as squares, maybe it'll make it easier. Times, and then the square root of a to the 4th. How is that a square, right? Well, using that power to a power rule, a to the 4th is a squared, right? That's how a to the 4th is a square, right? Something raised to the second power. And then we take the square root of our perfect squares, right? The square root of 2 squared would just be, the absolute value of 2, right, in even root. But what is the absolute value of 2? It's just 2, right? Times, and then the square root of a squared would be the absolute value of a squared. But let's think about that for a second. Again, off to the side here. The absolute value of a squared. When a is a real number, and we already said a is positive, by the way. A has to be positive. So a squared, no matter whether you're positive or negative for a, is going to be non-negative. So I don't need the absolute value around a squared. The absolute value of a squared is just going to be a squared, because a squared is already going to be non-negative. So I get 2 for that, and then the square root of a to the 4th, or the square root of a squared squared, is just a squared. No need for the absolute values, and there you go. That's completely simplified. Nothing else to do. All right. And again, let's test it out. All right, let's test it out. There's my original expression. There's the final one. I said they're equal. All right, so they should be equal for every value in the domain, right? Every value that's allowed to be plugged in, which is only positives, right? So don't do anything with negatives. The calculator will come back with an error if you put in a negative value for a, because you'll be taking the square root of a negative, and that's not real, a non-real answer. Okay, so pick a positive number. All right, say I don't know, 12. Let's make it 11. All right, so I'm going to plug in 11 for a. So that first expression, clear this stuff. I got the square root, and then inside that square root I have 12 times, and then I'm replacing a with 11 in this test. So 11 to the 5th. All right, that's in the numerator, so get out of that. Right now I'm, then after the radical divided by, right? It's the whole radical divided by. And in the denominator, you have the square root of 3 times a, or 3 times 11. Right, I'm replacing a with 11. And this number is, wow, okay, 242. Right, 242, nice whole number. Well, you could probably more have easily seen that if we said this is equal to this, which you're going to see when a is 11 is a nice whole number, a nice 242. Right, go to this expression here, we have 2 times, and replace a with 11 there, 11 squared. And look, that is 242. Fantastic, right? And it should be that way no matter what you plug in for a, as long as a is positive, right? So go ahead and try it out. Replace a with 5, 10, 15, a third, 2/5, pi, square root of 7, anything crazy. As long as it's positive, it'll be fine. They should be equal. Okay. My next example, we have a lot less to worry about, because look, cube roots, odd roots. So remember, you can take the odd roots of anything. But just as with the other ones, there's some variables here. Well, there's only one variable, x, right? There's an x squared here, and then down here there's an x to the negative first. And if I haven't mentioned it before, I'll mention it here. Recall that when you have something to a negative power, say a to the negative n, that's just the reciprocal of the positive power, so 1 over a to the nth. So can you see that the base on the negative power can't be 0? All right, so you can never have 0 to negative powers. Right? That's the same thing as basically dividing by 0. Right? So dividing by 0 and having 0 raised to a negative power are both bad. They're both undefined. Can't be allowed. All right, so let's get into the domain of this. Right? So again, let's what am I allowed to plug in for x? Well, because these are odd roots, it doesn't matter if the expression inside is negative or positive or 0. Right, you can take odd roots of anything. But the only thing really that I'm worried about here is, you see I have this variable to a negative power. And I just mentioned this over here. If you have an expression to a negative power, that expression, that base, can't be 0. So right here, I have x to the negative 1. X can't be 0. So x cannot be 0, but it can be anything else, right? A positive number to a negative power is okay. A negative number raised to a negative power is all right. And then up here you're just squaring stuff. I mean, so I can plug in anything else I want, and it doesn't matter if, again, what's inside the odd roots. Right? So the only number I can't plug in for x is the number 0. Everything else is fair game. Okay, so as long as x is not 0, these two expressions will represent real numbers. Therefore, I can put them together with this quotient property. So the cube root of negative 24x squared divided by the cube root of 3x to the times x to the negative first will be equal to the cube root of negative 24x squared divided by 3 times x to the negative first, that fraction inside the radical. And then we can simplify this, can't do some division. Negative 24 in the numerator divided by 3, that's 8, negative 8. All right, I have the cube root of negative 8. And then remember how this works, x to the second divided by, and then x to the second in the numerator, and then a factor of x to the negative first in the denominator. Remember that property of exponents. When you divide two things with the same base, you keep the base, right? So it'll be x to some power, and you subtract the powers, the numerator power minus the denominator power. So 2 minus negative 1, that's 2 plus 1. So that's x to the positive 3. Right? So this x to the second over x to the negative 1, that's x to the third in the numerator. X to the third, over 1. Right? And this one, these are nice perfect cubes, right? I'm taking the cube root here. I'm looking for perfect third powers, perfect cubes. Use that product rule. What's the cube root of negative 8? What to the third power would give me negative 8? That's negative 2, right? And then the cube root of x cubed would simply be x. Again, no need to worry about, do I need an absolute value or anything, because it is an odd root, right? You only need to worry about absolute values, and do I need absolute values around my answer if it's an even root. Right? And that's it, right there, negative 2x. And again, let's test it out. So I'm going to go into this expression here in my calculator, and then we'll just multiply whatever my number x is by -2, and it should be the same thing. All right, so here's the calculator again, and again, I can plug in anything I want except 0. All right, so how about, like, I don't know, 17? Why not? So I'm going to plug in 17 for x and see what happens. They better be equal. So that first expression I have in the numerator, the cube root of -24 times, and then I'm letting x be 17, right? So 17 squared. That's all in the numerator. And then outside that, we got divided by. And then in the denominator, I have the square root, or sorry, the cube root. The cube root of 3 times x to the -1st. So 3 times, and again, I'm having x be 17. So 17 raised to the -1 power. All right, let's see what we get here. -34. That was plugging in plugging in 17 for x in this first expression. And now let's do it here. We said this expression was equal to this one in the box. -2 times x, -2 times, and I'm letting x be 17. That is indeed -34 again. They are the same value, and that will always happen, right? For any value you plug in for x, except 0, right? You can't plug in 0. That'll be some undefined. You'll have something undefined. The calculator will come back at you with an error. All right, I've got just one more here. Very similar example. So here, another one where we don't have to do that much worrying. There are 2 variables this time, a and b, but notice how the roots are both odd roots again. So if they're both odd roots, you can just jump and use the product property right away. You don't have to worry about whether or not the radicands are non-negative or something, right? All right, so before I get into all that, let's talk about the domain of this expression. What am I allowed to plug in for not only a but b here, right? Okay, so again, these are cube roots, so I don't have to worry about these being negative or positive, right? You don't have to worry about that. So really all I'm going to worry about is, am I ever dividing by 0? Right? Do I ever have 0 in a denominator, or do I have 0 to a negative power at any point? And hopefully you can see down here, look at this. You have 2 times a times b in the denominator here in this cube root. If a were 0, that would be bad, because you'd have the cube root of 0, which is 0. You'd have a 0 in a denominator. So a can't be 0. Same thing for b. If b were 0, that would be bad. You'd have 0 in this denominator. Same thing here. If b were 0, you'd have 0 to the -2nd. You can't have 0 to a negative power. That's basically the same thing as dividing by 0. And that seems to be the only restriction I can come up with. Because again, these are odd roots. There's really no other restrictions to be had. So the domain is, as long as a is not 0 and b is not 0 at the same time, as long as you don't plug in well, actually, or I should put or, because if one of those is a 0, it's bad, right? So if a, as long as a is not 0, or b is not 0, or both, right? You're okay, right? Actually, no, it should be n. I apologize. My apologies, right? Both of those have to be true. These both have to be true, right? So it's got to be and. Because you can't have a be 0, and b be non-zero. Right? Both a and b have to be non-zero in order for this to be defined. All right, so sorry, that should be an and. My apologies. Okay, and anything else is fine. All right, you can plug in a positive number for a and then a negative number for b, a negative number for a positive number for b, both positives, both negatives. Right, again, it's just so long as neither of them are 0. Right. Okay, so as long as this is happening, as long as neither a nor b are 0, we can evaluate this. We can simplify this. Okay, These will both be real, right? They're odd roots, so it doesn't matter what you plug in, as long as, again, as long as A and B are not both 0. So I can use that, quotient property, that cube root of 250 a to the 5th times b to the negative 2nd divided by the cube root of 2ab. I can write as a fraction, the cube root of the fraction, where 250 times a to the 5th times b to the negative 2nd is in the numerator. And in the denominator I have 2 times a times b. And just as with the last example, I can simplify this fraction by doing some divisions. So this would be the cube root. The 250 and 250 in the numerator, 2 in the denominator, that's 125, right? You'd have 125 in the numerator. A to the 5th factors in the numerator, 5 factors of a in the numerator, 1 factor of a in the denominator. That makes a to the 5 minus 1, right? A to the 4th in the numerator. And here, b to the negative 2, over b to the 1, right? Just b to the first. As I mentioned in the last page, dividing two things with the same base, you keep the base, so b, and then numerator power, negative 2 minus 1. So b to the negative 3. Okay, b to the negative 3. And very often you'll see in I'm pulling these examples from an intermediate algebra textbook. Very often they'll ask you to rewrite things in the end so that you don't have negative powers. So instead of this b to the negative 3, or b to the negative 3 is the same thing as 1 over b to the 3. Right? B to the negative power is the reciprocal of b to the positive power. So all that's going to do is put 1 in the numerator with the 125 a to the 4th, and it'll put b cubed in the denominator. So I'm going to rewrite it that way, because again, very often you are asked to rewrite expressions so that there's no more negative exponents at the end. So I'd have 125 a to the 4th in the numerator, and then the b to the negative 3 is again 1 over b to the 3rd, so b to the 3rd in the denominator. And then yet again, right, even after writing this and rewriting without negative exponents, I can use that fraction property again. Say this is the cube root of the numerator, 125 a to the 4th, divided by, and then the cube root of b cubed. All right. And I'm taking cube roots, right? So what I'm looking for are perfect third powers, perfect cubes. And the numerator here, 125, the cube root of 125 is 5. 5 to the 3rd power is 125. The cube root of a to the 4th, a little trickier, right? Because the 4th power, that's not a multiple of 3, right? But it is bigger than 3. So when you're taking the cube root of a to the 4th, you can split up a to the 4th so that it is a perfect cube times a non-perfect cube. I can split that up to the cube root of, and then a to the 4th is, a to the 3rd, that's a perfect cube, something with a power that's a multiple of 3, times a to the 1st, right? That's the same as a to the 4th. And the cube root of a cubed is a, and then you'd have still just the cube root of a afterwards, right? The cube root of a cubed is a times, and then just the cube root of a, the cube root of the non-perfect cube after. So going back up here in my numerator, right, the cube root of 125 is 5, and then the cube root of a to the 4th, as you see down here, is a times the cube root of a. Right, and notice, don't need to worry about, do I need an absolute value around the a? No. It's a cube root, right? You don't have to worry about that with odd roots. Alright, then divided by, and then the cube root of another perfect cube, the cube root of b cubed is simply b. And again, no need for absolute values. This is not an even root, it is an odd root. And there you go. And the numerator and denominator have no common factor. Alright, so that's as simple as that gets. Alright, so again, let's test it out. This is the last one. Let's test it out. This time, since there's multiple variables, I'll keep track of it on the page. So again, as long as neither one of them is 0, As long as A is not 0 and at the same time B is not 0. Right? As long as neither one of them is 0, the expression I started with should have the same value as this expression in the box here. So I'm going to have A be, say, positive 3, and I'll have B be, I don't know, negative 2. And let's see what happens. All right, let's see what values we get. Again, as long as they're not both 0. All right, so I bring my calculator in, and let's check it out. So the first expression I had, we had in the numerator the cube root of, and then inside that cube root you had 250 times, and then a to the 5th, but I'm letting a be 3, right? So 3 to the 5th times, and then b to the negative 2nd, and I have b is negative 2. So in parentheses negative 2, then that number raised to the negative 2 power. All right, and then get out of that radical, right? That's all in the numerator, and then after that divided by, and then the cube root in the denominator, cube root of, and then inside that cube root 2 times a times b, 2 times 3 for a times, and then negative 2 in parentheses for b. And let's see. So that's negative 10.81687178 blah 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 blah. It goes on probably forever without ending or repeating. Probably irrational. All right, now let's check this other one in the box. See what happens when a is 3 and b is negative 2, and if hopefully I get the same value. All right, so the numerator has multiple factors. I'm going to put that all in parentheses here. We have 5 times a, which I'm replacing with 3, times, and then the cube root of a, which is 3 again, cube root of 3. All right, get out of there. That whole thing is the numerator of this expression, where a is 3. And then afterwards divided by, and the denominator is negative 2. I'll put in parentheses negative 2. And hopefully, right, if I did everything correctly, these should have the same value. It should be that negative 10.81687178, and there it is. Right? They are the same value. Wonderful. And try it out with any other combination of a and b. Right? Have a be 10 and b be negative 3/4, and have a be the square root of 5 and b be negative 20. Whatever you want. Again, as long as they're not both 0. Right? Okay. All right. So as I like to say at the end of these videos, try the best you can to learn the material on your own before you go looking for help. I find that when people take the time and the effort to learn something on their own, they remember it better and for longer. More proud of it. So of course, read the material, read through the author's examples. Perhaps even try to work out the solutions to an author's example before you see how the author did it, and then compare your work with the author's and see if you can learn from some mistakes there. Obviously work out many exercises, practice problems, look for solutions to those if they're provided to you, so you can check your work and track your progress. And of course, don't give up on an exercise or a problem just because, after the first attempt. Don't give up so easily. Very often, there are several approaches in mathematics that will work for any particular problem. So, I mean, if after several approaches at a problem, you're still not getting it, still not understanding how to do it, maybe you should go back and read the material again, maybe even a third time, more slowly, more deliberately, take notes. Because if you've been doing some problems, the chances are you have a better idea as to what the author expects of you, what the author wants from you. So, when you go and read the material again, maybe the third time, you'll have a better idea as to what to look out for. Maybe you'll catch some things that you didn't catch the first time that'll make things that much easier to understand. But if after that, if after several read-throughs of the material and several attempts at problems you're still not getting it, it is not a sign of weakness whatsoever to go out looking for help. That is what other people are there for, to help you. So ask a teacher, a tutor, a friend, someone in your class who you know knows the material well and is willing to help. Look for supplemental materials online. There's loads of it out there. Look for videos online. Tons of those too. Videos like this one, or plenty of other ones out there better than this one. I assure you they're out there and you can find them easily. But just keep at it. Stay persistent. Keep practicing. Don't give up. And above all, and I think this is the hardest part, try to have a positive attitude toward the subject. Believe in yourself. Have an open mind. Think you might even have fun with it. I know it's easier said than done, but you'd be amazed at the difference a little change in attitude, a little positive thinking can have on the learning experience. So, stay persistent, keep practicing, stay positive, and don't give up. Don't ever give up. And I just know you'll get it. Thank you very much for watching.